This video discusses the concepts of scatter plots and correlation found in section 4.1. In chapter 4, we're going to look at bivariate data. That means data where we have two variables for each individual in the data set. That means for every individual, we have an ordered pair, and the graph of ordered pairs is called a scatter plot or scatter diagram. You've graphed ordered pairs before. Here's an example to remind you how it works. We graph the first number on the x-axis, the horizontal axis, and the second number of the ordered pair on the y-axis. When we have two numeric variables that are related in some way, we say there is a correlation. This only applies to numeric variables. If the variables aren't numeric, then we can say they're associated, but we can't compute a correlation coefficient, so they aren't correlated, only associated. In this class, we will use a linear correlation coefficient to measure the strength of the linear relationship between the two variables. To compute the correlation coefficient, we must have paired data, and it must be quantitative data. This is the formula for the correlation coefficient, and you don't need to know this or use this formula. We have a calculator function that will compute this for us, and there's a separate video to show you how to do the calculations. If you want to learn to compute this by hand, you can see the steps in the book. However, notice that first you'll need to compute the mean and standard deviation for both variables separately. This is why it's much better to use the calculator function, because it's less time consuming and because there is less room for error. Notice that R is our symbol for the sample correlation coefficient. So what do we need to know about the correlation coefficient? The value of R will always be between -1 and 1, including both numbers. An R of 0 means no correlation. An R of 1 means all the points fall perfectly on a straight line with a positive slope. An R of -1 means all the points fall perfectly on a straight line with a negative slope. The closer the R is to 0, the weaker the correlation. The closer the value is to 1 or -1, the closer the data will be to the straight line. In the homework and on quizzes and tests, I might ask you to describe the correlation that you see in a graph. So let's discuss how to describe correlation. Two variables have a positive correlation when large values of one variable correspond to large values of the other variable. Or in other words, when we look at the scatter plot, the line will have a positive slope. Let's look back at our example. If we draw a line through these 4 points, we see that the line has a positive slope. We also see that as the x value increases, the y values also increase. So this is an example of positive correlation. When I compute the correlation coefficient, it comes out to be 0.89, which is fairly close to 1, and that makes sense because the points are close to the line, but not exactly on the line. Next, we'll look at negative correlation, when large values of one variable correspond to small values of the other variable. Or in other words, the line through the points on the scatter plot has a negative slope. We'll look at an example. When we draw a line through these 5 points, the line has a negative slope. As the x values get larger, the y values get smaller, and vice versa. These points don't follow the line exactly and are a bit more spread out than our previous example. Here, the correlation coefficient, R, is negative 0.65. A zero correlation means that the two variables aren't related to each other in a linear way. Here is an example of 5 points with no linear correlation. When I draw a line through the points, the slope is 0 and R is also 0. However, it's important to remember that the linear correlation coefficient only measures a linear relationship. Maybe there is a parabola that will explain the relationship. Maybe these points are measuring the height of a punted football over time. It's very important to look at a scatter plot and be sure that the line is the most appropriate way to describe the relationship between the variables. Besides describing a correlation coefficient as positive, negative, or zero, we also want to describe the strength of the relationship. For values close to 1 or negative 1, we say the correlation is strong. For values close to 0, from about negative 0.25 to positive 0.25, we say the correlation is weak. In between, we would say that the correlation is moderate. So let's practice identifying correlations. Here are some correlations I generated in Excel. This first example is positive and close to a straight line, so we would classify this relationship as a strong positive linear relationship. In fact, for this example, the correlation coefficient R turns out to be 0.98. Let's look at another example. What do you think? Positive or negative? Strong, moderate, or weak? This is an example of a moderate negative linear correlation. Here, R is equal to negative 0.67. Our last example. What do you think? Positive, negative, 0? When I generated the data in Excel, I generated random data to try to get zero correlation. You might think you see a slight pattern, but there isn't a pattern here. Though the correlation coefficient isn't exactly 0, this is still zero correlation. The correlation coefficient is negative 0.04. So how big does the correlation coefficient need to be before we can decide that there's actually correlation? It depends on the sample size, and we'll talk about this more in class. So let's review. First of all, to compute a correlation coefficient, we must have numbers, and they must be in pairs. When we need to describe correlation, we describe it as positive, negative, or 0, and also as strong, moderate, or weak. Once we know two variables are correlated, we can use the relationship to predict values outside the data set. We'll look at how that works in the next video.